Welcome to another video for Stat 212. In this video, we're going to talk about probability distributions. And a probability distribution is really still a probability model. It's usually just a more specific term that we might use when we're talking about the probability model for a continuous, or at least a continuous-like variable. So the terms are almost interchangeable in a lot of ways. However, if I can't necessarily represent, or I wouldn't necessarily represent a probability model for a variable with, say, a table, but instead maybe there's enough categories, or if the variable is truly continuous, I instead might represent the model with a distribution curve or with a density curve. And so when we get to that point, we're more likely going to just start calling it a probability distribution. So for example, down here, this tells us the different values that a random variable can take. And now it's going to be visually represented, where the height of the curve is telling us how likely we are to observe outcomes in that range. So in this case, we're not really going to represent this with a table, but a distribution curve would make a lot more sense. So a couple notes to make here. If we're looking at a density curve for a random variable, the area under the curve should add up to 1, or 100%. So it's kind of representing then the full possibility, where again the height of the curve means it's more probable, a lower part of the curve means that we're less probable to see observations in this range. And to find the probability of a particular range of outcomes happening, we would just find the area under the curve for that particular range. Now, if we're working with truly continuous data, you might remember that there is an infinite level of precision, meaning that that we can't exactly find the probability of a very, very specific measurement, as much as we're really just going to find the probability of a range of measurements. So for example, if we're talking about height, when we say that we can't really find the probability of a very specific measurement, that's because if we think about an infinite level of precision, we don't really know the probability of somebody being exactly 66.00000 inches, or really what we'd say is the probability is approaching 0 if it's an infinitely precise measurement. But we could find the probability of somebody being between, say, 65.75 inches and 66.25 inches. So when we say that somebody's about 66 inches tall, usually we're just kind of making a round or an estimate there. And the probability of somebody being about 65 inches tall is really the probability that they're in that kind of range around 66. So if we were doing a probability and statistics course like a Stat 400, then we could use calculus, and specifically integration, to find the probability of a particular range of outcomes by finding the area under the curve. In this class, we're not using calculus, so we're just kind of mentioning it as an aside that we're working with continuous variables. The probability is just going to be the area of the curve between those two values. So the extent to which we'll practice that is with an example like this, where on the right we see a density curve, and we can see within different ranges the area under the curve that's within those ranges. So according to the density curve on the right, what is the probability of getting a measurement between 15 and 20? So I would just look over here, and I would notice that between 15 and 20, about 34% of the data appears to be in that range. So I'm going to say 34%. I could also say 0.34. That's fine, as long as I don't say 0.34%. That would not be the same, but 34% or 0.34, either of those would correctly describe that probability. What is the probability of getting a measurement above 20? Well, that's going to be the area under the curve past this point. So it's going to be this sector plus this sector plus this sector as well. So that's going to add up to 0.41 plus 0.21 plus 0.03 is going to be, I believe, 0.65 or 65%, if you'd rather write it like that. So again, that is the extent to which We will do areas under the curve. It's just identifying from a picture, but we won't be using calculus in this course. So let's talk a little bit more about common distribution shapes. We have talked before a little bit about how common distributions might be symmetric. Some of them are asymmetric. Some of them have multiple peaks. Some of them only have one peak. Sometimes distributions are more skewed, right? So we've talked about a little bit about shape before, and now we're going to talk about kind of a couple categories that we're going to work with. And the first one that we're going to talk about is a uniform distribution. And we're going to think about what kind of random variables would have a uniform distribution. So a uniform distribution means that all possibilities for that random variable are equally likely. So if I pick out any equally spaced range, it should be equally likely to occur. So if I think about, say, rolling a six-sided die, that's not a continuous variable, but we would say that a six-sided die has a uniform distribution, where 1 through 6 should be equally likely. So we could do the same thing when we're talking about continuous variables as well. So here's an example where we're talking about we're letting this random variable be the amount of time that someone might wait at a stoplight. And let's say that one particular light remains red for 90 seconds. So assuming that that light is red when I pull up, then I will wait anywhere from 0 to 90 seconds. And that should be represented approximately with a uniform distribution. Possibly there might be a little bit of a change right over here, depending on, if I'm arriving right as it's turning green, or maybe at the end. But for the most part, it should be about uniform for most of that 90 range. So you can kind of see this graph on the right demonstrates wait times under these conditions where I did, I think I did more than 2,000. That's probably, it might be like 2 million maybe. I'm not really sure honestly at the moment. It looks like I did quite a few simulations of this and then created a uniform distribution to kind of show over time. We would see that each of these bends should come up about equally likely here. So one nice characteristic about uniformly distributed data is that it is symmetric about the mean. So if my data is uniformly distributed from 0 to 90, then that means that the mean, as well as the median, should be 45 in that case. Another nice characteristic is that the percentage of data in any given range would just be that range divided by the total range of outcomes. So if I think about it, I have an example right here. What is the probability that I will need to wait at this red light for more than 35 seconds? So we can calculate that by finding the range of the area of interest divided by the total range possible. So if I'm interested in the probability of waiting more than 35 seconds, I'm going to do 90 minus 35 divided by the total length of the range, which is just going to be 90. You might be wondering, since it says more than 35 seconds, does that matter? Should I say 36 seconds? Should I say 35.1 seconds? And when we're working with truly continuous data, it really doesn't matter. So if we're saying more than 35 seconds, then really any value, 35.00001, would technically qualify. So it'd be most appropriate then to do 90 minus 35 here. So we can calculate this, and we're going to get 55 over 90, which is going to come out to some value. Let's see. I'm going to get 0.611 there. So about 61% of the time, I'm going to have to wait more than 35 seconds at this red light. That's a reasonably long red light. Most red lights are probably a little bit shorter, but if this one's always 90 seconds long, then I should expect to wait a little bit of time there. Here's another one. This one's set up a little bit trickier to kind of get you to think about it. I'd encourage you to pause the video for a second and see if you can solve it. But here we have a woman arrives at her bus stop at random times, and the particular bus she waits for comes at 20-minute intervals. She also knows that it takes exactly 15 minutes for the bus to drive from the bus stop to her destination. What percentage of the time will she arrive at her destination within 30 minutes of arriving at her bus stop? I feel like this is a really great question for me because I typically ride the bus to school, and if I don't use my bus tracker, if I just go at a random time, then I kind of have to keep in mind how much maximum time could it take for me to get to my office or to get to class or something like that. But I'd encourage you to pause and think about this one first. All right. So I would just start by noticing that the entire so I'm interested here in um, how long it takes to get to her destination after arriving at her bus stop. And so if I think about the maximum amount of time involved in this question, it would be 35 minutes, right? So there's 20 minutes for the bus stop plus an added 15 minutes. However, there's also a minimum time for her to get to her destination. So it's not uniformly distributed from 0 to 35. It's going to be uniformly distributed from 15 to 35, right? So at minimum, she gets there in 15 minutes. At maximum, she gets there in 35 minutes. So for that reason, I'm going to put 35 minus 15 in the denominator. And then I'm going to put 30 minus 15 in the numerator. So again, the logic here is she wants to know if she's going to make it within 30 minutes. So that means that she's going to be in that 15 to 30 range. And I also know that the total possible is going to be the 15 to 35 range. So then the probability that she makes it in that time is going to come out to about 15 over 20, which should be about 75%. So again, if you think about this logically, you can kind of track this here that 25% of the time she'll make it in 15 to 20, 25% of the time she should make it in 20 to 25, etc. So maybe that also helps you kind of think about it. But this one, again, it's set up a little bit trickier. You have to think about exactly what you're dividing from what. But once you do, it is a uniform distribution that we're working with. I'll also draw a picture too. So she's going to make it anywhere, and that's not exactly the same height, unfortunately. Just pretend it is. She's going to be anywhere from 15 to 35, and this is kind of the range that we found there. All right. Oh, and that was the last thing for this video, so we'll stop there.